Hello everyone and welcome back to the actual lecture material for what would be lecture 5. In today's videos we are going to be finishing up talking about chapter 2, which is plate tectonics, and then we're going to be going into chapter 3, which is looking at the ocean floor and various marine provinces. So there's there's at least one extra video that I think is pretty cool that we would watch in class. It's a TED Talk, so I will link that separately, as opposed to watching it here. There will still be questions regarding that video in your homework for this week, so do just make sure that you watch that. Yeah. Here we go. This video is also going to include an explanation of how to do the one calculation that we're going to do in this class. It's called the rate of spread calculation. So I'll work through the example that I have on the slides here, as well as I will have extra rate of spread walk through for a different example. And then also when we come to class together, then we'll walk through another example or two as a group. So just know that we have several different resources for us, okay? So don't freak out. Okay, on to it. So we started talking about hotspots in class. If we recall, we've been talking about these different plate tectonic features, things that we see at various regions. And one thing that is not at an edge of a plate boundary are hotspots. So maybe you've wondered to yourself, oh dang, look at Hawaii. That's pretty interesting. It looks like a chain. It looks like maybe they're connected somewhere underneath. And really what happens is they're over, or used to be over a hotspot. So that's what we see in this diagram here. So we have Kauai is the most northwestern island, and then the big island of Hawaii, which is the one that's currently close to the closest to the current hotspot, is the Big Island. So the Big Island also has several areas where there is still volcanic activity going on right now. Maybe you heard earlier, or at the end of 2021, there was another pretty big eruption on the Big Island with lava flows and things like that. It's because it's really, really close to that hotspot. So what's pretty cool, actually, I think, and we'll learn further about this later on, but as the plate keeps moving, and that's what this red arrow is indicating, that movement to the northwest of the Pacific plate in general, but the hotspot stays in the same place, right? So from here we can discern that basically the island of Kauai is the oldest of all of the main islands of Hawaii. And if we were to look underneath the surface of the water, we would actually probably be able to see further islands that are just some things that we call seamounts or guyouts. These are basically islands that are underwater. They don't have any tips sticking up above the water. What's kind of crazy is it turns out sometimes that islands can actually be above water for some of their life. And then as they're still connected to the bottom of the plate, and as they move, as the plate continues to move, then the island actually ends up kind of sinking back down into the water, which is really quite fascinating. And there's actually some consequences or some features that we will learn about later on, like coral reefs and atolls that are built around these islands sometimes, and then the island goes away, but then those other features stay there. So what we see on this bottom part of the graphic there's years associated with these various islands, basically saying how old or young we believe some of these islands are. And so we can take these ages and we can take the distance between these islands, and we can literally calculate how fast that plate has moved over its lifetime. So I have 3 simple steps to help show us and give us these the answer here. So the biggest thing first thing to do is kind of figure out the plate of motion, basically just use the ages of the islands. So in this particular example, our youngest island is 0.1 million years old, but our oldest island is over here to the right-hand side, and it's 8.2 million years old. So because the oldest one is over here on the right, then we could assume that the plate is going kind of up and to the right a little bit, or, if we're looking north, south, east, west, it's going to the northeast. And then from there, you calculate the spreading rate or the rate of plate motion for that area, and then you're going to convert your answer to centimeters per year. So I have some pretty straightforward steps here. The first thing is going to be subtracting the youngest island from the oldest island. And, remember, we're in millions of years here, so it's good to expand our millions of years, which is in a sense in scientific notation, and expand it out of that. Then convert the distance, the kilometers here, convert that to centimeters, because the answer I want you to have is in centimeters per year, and then divide that distance over years. And that would be your rate of spread in centimeters per year. So we're going to walk through this example. I'm going to make my face much bigger here. Hi, hey, hello. And we're going to walk through this together and see how I can get a way that will work here. Okay, so we have step one, which hopefully this is, okay, perfect, is to subtract our youngest from our oldest. So our oldest island was 8.2 million years minus 0.1 million years. So if we do that calculation, and you won't need any fancy calculator, you can just use your phone. So even though I can do this in my head, it's fine. 8.2 minus 0.1 is equal to 8.1 million years. So if we expand that out, that is equal to 8,100,000 years. So that's step one. Step one. Whoop, whoop, there we go. Step one. Expand the years out. Excuse me. Step two is to then convert the distance from kilometers to centimeters. Kilometers to centimeters. This is a two-step process. And this is a way that I do conversions that's been very helpful for me. I learned it in high school chemistry. I think it's pretty straightforward. If you know another way to do conversions, go for it. But basically, we have 1,220 kilometers. And something that I like to do is a little T chart here, like it's a sideways T. And in order to convert from one to another, we just have to have our conversions out there. So in 1 kilometer and 1 kilometer is 1,000 meters. Notice how my kilometer, I have 1 kilometer I have kilometers in my numerator, if we were to put this over 1, and a kilometer in my denominator. So these two units can cancel. And then in 1 meter, we have 100 centimeters. All right, so we just multiply across, and an easy way to do that is just to add zeros. So I'm going to do 1,220 plus 1, 2, 3, 1, 2, so I multiply across, and then just add in my commas. So 1,220 kilometers is 120 million centimeters. Seems like a lot, 122 million centimeters. Seems like a lot, but it's a long distance. And then our last step here is to divide our distance over our years. So 122 million centimeters per 8,100,000 years. Again, if you were taught how to, kind of do, Xing out your zeros here, then it could be a pretty straightforward thing. But for me, I like just typing it out or writing it out individually, because I'm just a visual person. It works out for me. So if I were to say, so this comes out to be 15.06172, etc. And I will ask you in any assessment to round to the nearest tenths place, which is one spot to the right of the decimal. Okay, so in this case, this answer would then round to 15.1 centimeters per year. 15.1 centimeters per year. So that is the answer for this problem. So again, we will have, we'll do more examples in class. I'll have a separate video up and ready for you to do that. But that's just working through the one that is here on these lecture slides. Okay. So if you have any questions on that, please reach out. Alrighty, so these are just some examples of potential questions on plate motions. So just things that we've talked about throughout this whole thing. Basically, considering pairs of cities that are either getting closer together or further apart. Considering what's happening to the sides of the Pacific, the Atlantic, and the Indian Ocean, just again from the movement of the plates as they are currently moving. And then describing the types of plate boundaries that exist along the west coast of North America and how you know that, right? Like what are some of our geological features that tell us what plate boundaries we're on, especially considering San Francisco in particular. And then describing the tectonic setting on the east coast of North America. So what's kind of cool with some of this stuff is we will journey into some of the other consequences that we would see actually under the water as opposed to above water. So last thing I want to have for us for this video is just an overall review of our first two chapters. We've already gone over a pretty decent amount of material, and I snagged these just straight up from our study guide or guided notes / study guide, whatever you want to call it. So yeah, so basically, how much land versus water do we got? How big are our world's oceans? The average depth, which one's largest and smallest, deepest and shallowest? And then going into plate tectonic theory, the biggest question you're going to have, especially on your exam, is going to be looking at a short answer question of the history of plate tectonics. And then, of course, the 3 plate boundary types and the features that are located at those boundaries. And then what we just finished with today, which is how to calculate a hotspot. Also, do keep in mind that, or recall that your book does not go into accreted terrain or why that's important, but we did go through that in class. So please make sure that you understand that as well. That will also be another short answer question on the exam. All right, so when we come back, we will talk about the ocean floor and the marine provinces. All right, thanks so much for watching. Ooh, I'll make my face bigger for just a second. Thanks so much for watching. Cheers.